Well, hello everyone, and welcome to this webinar on Rhino3D for building performance. My name is Nagman Khan. I'm delighted to be hosting my second webinar with EDSL. And some of you who joined our webinar earlier in December might remember we had a lot of questions around using Rhino, the Grasshopper Ladybug tools ecosystem with TAS. So we thought we'd develop this webinar quite quickly, and Ian and Andrew have turned it around very impressively. So we're keen to show you some very cool stuff. With that said, let's meet the speakers for today. I'm going to hand over to Ian and Andrew to introduce themselves quickly, and then we'll have a look at the agenda. Ian, welcome.
Thank you, Nagman. Hi, everyone. Ian Heighton, Technical Director at EDSL. I've been here since the start in 1989, so that's 30-something years. My original background is maths and computing, so mostly worked on development at EDSL and particularly the CFD, which hopefully we can see a little bit later on. Thanks, Andrew.
Yeah, no worries. I'm Andrew, so I've been with EDSL for about 11.5 years now. I've got a background in physics, and when I started at EDSL, I started in the consultancy services department using the software, and then I transitioned to the development team. So I get to create the software and help support it, add new features and things.
Amazing. Let's look at the agenda quickly. So I'm going to hand back to Ian very quickly to introduce TAS engineering to us for those of you that are new to the software. And then Andrew will take us through a demonstration, including a live demo of importing Rhino CAD into TAS using Honeybee and a couple of other cool scripts that he's put together. And then back to Ian for a quick look at the 3D CFD engine, Ambience 3D. And please keep your questions coming through the Q&A panel, or you can also use the chat functionality here in Teams. It's good to have a chat, keep the conversation flowing during the webinar. We'll consolidate all the questions and take them together at the end. I'll hand over to you, Ian.
Oh gosh, yeah, sorry. Yeah, TAS was originally developed a long time ago at Cranfield Institute, as it was back then. So we're talking 1973 and 1979. I was still a school kid at that point, so not involved in those processes. It was primarily developed because there was an oil crisis in both those years, 73 and 79. So suddenly energy performance and saving energy and not burning quite so much oil or being quite so dependent on oil was quite a significant thing. And that's effectively what kicked it off. The second phase we got obviously was 2006 when Part L EPC stuff arrived in the UK as a response to the European directives on building performance. So yeah, it's been through a few phases, had a lot of input from Legal & General, which is a big insurance company in the UK, made massive strides, and eventually that sort of fizzled out, and that's when we formed EDSL to carry on the development of TAS since 1989, and we've been doing that ever since. So that's the potted history of TAS. Okay, so we've been, pioneer is probably quite a good word to use, but TAS has pioneered quite a few technical advances over the years. One of the first things, sorry, you can read through that list while I'm talking. One of the first projects I worked on was the power gen headquarters. We're going back decades here, but it was very unusual at the time because it was a fully naturally ventilated building. So this was the very first time that we actually had to integrate bulk airflow. So this is, outside pressure coefficients leading to air movement through the network inside the building, plus obviously the buoyancy forces, giving you that sort of bulk air movement and integrating that with obviously the thermal analysis that was going on at the same time. So yeah, that was, I think, the first time we ever did the fabric and the air movement at the same time. Another prestigious building we were involved in, the Gherkin, 12 St Mary Axe in London. That was a very complicated mixed mode building where if a single floor, they'd obviously run it as natural vent if they could, but if a single floor went above a certain temperature, then they'd shut that floor down into air conditioning mode, and obviously the rest of the building would try and carry on in natural ventilation mode. So that was a tough one, and we also got involved. This is not such a great project, but an interesting one. The funny little pods, the London Eye, which is that sort of big Ferris wheel in central London, those glass pods have got their own little air conditioning units in them, and they were obviously quite concerned that people might roast in there because they're basically mobile greenhouses. So sizing that and getting that energy correct was kind of important. And a little known fact, which we got wind of. The first few weeks that the London Eye was running, they actually had a mountaineering team down at the bottom just in case it broke or failed, and they had to send the mountaineers up to get people out of the pods. But I think they've got rid of the mountaineers subsequently once they realised it was pretty reliable. Yeah. So yeah, good. I think I'm going to hand over to you, Andrew. Is that right?
I think you were going to take this one, but I can take it if you want.
Oh, sorry, I had you down for this one.
Well, no worries.
I won't flip a coin for it.
Well, I was just going to say, TAS has been around for quite a long time, and TAS has quite a powerful API. We've got lots of integrations with different packages, and this is something that quite a lot of our customers, especially our bigger customers, really value. For example, the ability to get information in and out of Excel via macros. They find that very useful, and the optimization that we have in the software as well. Anything that you can do with the UI, you can optimize with our optimization program. So as you know, the focus of this webinar is to look at Rhino integration. So before I dive in and start showing you Rhino and Grasshopper, let's just have a quick overview of what TAS is like to use and what a typical workflow might look like in case you're not familiar. So generally speaking, you'd start in a 3D modeler. This is where you draw your geometry, and you can also do daylight calculations here and do shading calculations, and then you'd send that geometry to the building simulator. Then once you're in the building simulator, you'd add internal gains and construction information, you'd specify a weather file, and then you'd simulate that file to produce a results viewer file. The results viewer file has the temperature information for all the zones and surfaces, as well as load information, and you can look at airflow for natural ventilation studies, pollutant, things like that. And then from there, you can, if you want to, go onto the HVAC modeling program to model your HVAC system in quite a lot of detail. Or alternatively, you can go into Ambience 3D, which Ian's going to show you later. So you can look at the airflow in more detail in the space. Now, you can add geometry to the 3D modeler from external sources. Usually we do that via GBXML or IDF, although there are a few other formats that we can import too. But GBXML and IDF are the relevant ones for this talk. So we can also import.
Sorry, Andrew, just in terms of Rhino, we're talking via Honeybee, is that correct?
Yeah, exactly. So I'll show that on the next slide, but there are alternatives that you can use to get geometry into those formats ready for us. But shade surfaces, yeah, we can import those using 3D DWGs, and that's useful for shade buildings, but it's also useful for if you're trying to model detailed external shades adjacent to a window. And then again, we have the API for bidirectional data flow. So each of these core applications has the API, and that's useful not only for getting data into TAS, but also if you want to display those results that you've got from TAS back into Rhino or into another package. So I'll show you that a bit later too. And then once you've got everything in TAS, you can go off and do all these various types of analysis. I mean, there's quite a lot of them, from overheating to energy, TN54 neighbors, daylight calculations, or optimization programs and regulations. So, and there's probably quite a lot more that we haven't got on this diagram because, the software has been around for quite a long time now. So there's quite a lot that you can do with it.
It's also worth pointing out, sorry, Andrew, to butt in quickly, it's also worth pointing out that a lot of this development has come from the fact that we not only develop the software ourselves, but we use it for consultancy in-house. So quite often a lot of the development work is driven by projects that have come through the door and we've had to perform. Yeah. Sorry, Andrew.
Exactly. No, that's all right. So I'm going to be using Honeybee in this demo just to get the GBXML file that we can import into TAS. And I will also show you IDF as well, but I'll start with the GBXML. But I think there's other tools that you can use, such as Pollination. I think they produce an IDF file as well. That should be able to go into TAS, no problem. So Honeybee, I'm sure most of you are familiar with it, but it's a Grasshopper plugin, and it's part of Ladybug Tools. And under the hood, it uses OpenStudio to do energy analysis and generate GBXML and IDF files, and also import them. And you might be wondering, why bother using TAS if you've got energy analysis as part of OpenStudio? I would say the main reasons would be the speed, because TAS is quite quick to simulate, and also it's fully accredited, so you get access to the latest building regulations. You get access to the RCFD package, which is definitely unique. And again, the API makes it quite a lot easier to work with. And of course, if you have a TAS license, you get full software support. So because we developed our own engine, if there's a problem or a question you have about the software, you can just contact us and get a quick response. So that's quite valuable, I think. So I'll just jump into Rhino quickly to show you my setup. If I can find it, got quite a few programs open here.
Yeah, generally in meetings, Andrew's taskbar is quite terrifying.
Yeah, sorry about that. So yeah, I'm just going to show you a very simple geometry initially, but obviously this will apply to much bigger buildings of any size, really. I'll just start with something simple so you can see the concepts involved. So I've just made 3 boxes here, 3 cubes, cuboid, and this is my Grasshopper script. So all I've done is I've created a room solid here, Honeybee room solid, where I've connected up these geometries. And then I've solved the intersections. And the reason I've done that is so that we get matching faces between the zones, and that way we get heat transfer between the zones. They don't come across as adiabatic. And then I solve the adjacency for that, yes. And then I add apertures by ratio, so I add some windows to the building, and then I pass that to the model object, so I can create the Honeybee model. And then from there we have the two different pathways we can take. We can create a GBXML file using the dump GBXML component, or we can use the model.osn component, which can produce an IDF file. So if I turn this on and hide,
IDF's preferable because that's also got the construction and internal condition stuff in it. Is that right?
Yeah, exactly. So even though GBXML can specify construction information and internal conditions, if you use the IDF route, then that comes automatically into TAS. But the two, from a geometry point of view, the two are very similar. But yeah, the IDF is advantageous if you want that extra information to come across. So as you can see here, this is quite a simple model. And I will generate the GBXML file by toggling this on. And then I'll show you how that comes into TAS. So I think I have TAS 3D open. There we go. So once you've got TAS 3D open, our 3D modeling program, you just go to import and press GBXML and select the GBXML file. And then you're presented with 2 windows here. So you can see a preview of the geometry that's going to be imported, and you can see this import report. And the import report is quite useful because it tells you any issues that TAS 3D has detected whilst it was doing the import. So for example, you might have surfaces which have the wrong orientation, or you might have small gaps in the model, and TAS 3D will try and automatically fix those things. And if it does need to fix anything, it will tell you what it's done, so you're aware of the issues in case you need to go and fix them in the source geometry, or in case it makes an assumption that isn't right. But generally, from Honeybee GBXML files, I haven't really seen any issues with those at all that I can think of. You do sometimes see issues with Revit GBXML files, but it's been very good with Honeybee so far. And then you also have this dialog here. So this shows you the zones that are going to be imported. But if you go to the display tab, then you can inspect the geometry in a bit more detail to see what's going to come in. So for example, if I unselect ceilings and roofs, then you can see I've got the walls selected here. I can turn the floors on and off, and that's quite useful because again, you can quite easily see if something's not quite right. One of the surfaces got one of the wrong types. And if I change to color by analysis, then we can also see the boundary conditions and the types of surface that we've got. So for example, here, I can see the green one's exposed, so they've got the external boundary condition. But then we've also got this pink color here, which is the link color, to show that there is actually heat transfer between these spaces. So that's quite useful. So I'll press OK to import that. Even on very large files, the import's very quick. It's almost instantaneous. Yeah, so here's our geometry. And then if I want to, I can press this button here to create plans for editing. And this is quite useful because you can do things like you can alter the zoning. So for example, if I wanted to split this space, I could use a null wall, which is in some packages is known as an air wall, and I could subdivide this space. And then I could change the zoning if I wanted to. I could make a new analysis zone and split this into 2 zones, for example, and that can be quite useful. The other thing I can do as well, if I take the imported windows, for example, I could edit these imported windows. I could say give them a frame percentage of 10%, and therefore when you get into the building simulator, you can assign a different construction to the frame pane, so you get more accurate building simulation results. So if I leave this open and I go back to Rhino, and I change, let me turn this GBXML toggle off. If I change the size of the windows, say, let's make them narrow. There we go, narrow all windows. And then I update my GBXML file. I go back into TAS 3D. Then if I click import GBXML again and select the new GBXML file, TAS 3D will ask me if I want to update the existing building geometry. And what it will do in this case is it will try and remember the changes that I made to the model and reapply them. So as you can see here, it's remembered that I added that 10% frame. So I know ideally in you should be doing all these things in the source package, but if for some reason you do need to make a change in TAS 3D, we do try and make your life easier so you don't have to keep repeating work. So that can be quite useful. So now I'll show you, I'll just make a new file here. Now we'll take the other pathway, so I'll turn that one off, and I'll generate the IDF file. So that's just been generated there. Copy that and go back into TAS 3D, and we've got someone in the lobby. Insert them in. So if I click import IDF instead, then I can select my source IDF file. I can give it a name. I guess I'll keep it at the current name, and I'll put it in this folder. And then I can tick this box to have a building simulator file created too from the information that's in the IDF file. And I can say what I want it to bring in. So I'm going to say bring in internal conditions, model the internal mass, model. I'm going to import the unused constructions as well because it's useful for visualization purposes. And then I'm going to select an EPW file. I think I have one in my downloads folder. I'll press import. This is the bit where I find I'd left the TBT open and it's not going to work. Oh, there we go. So again, this looks very similar to what we had before from the GBXML import, but here's the colors are just slightly different. But again, it's pretty much exactly the same. But interestingly now, if we look in the output folder, we have a building simulator file which has been created. So in here, we can see that it's created a file with weather. We've also got the building elements that have come through. We've got a list of rooms, and we've got our internal conditions, which have heating and cooling set points. We have our constructions. So one thing that I'd like to draw your attention to while we're in here is the visualization, because this is a really useful tool. So, oops, what have I done? There we go. So if I open the visualization here, this is really powerful because you can select things in the building simulator and see where they are in the model. So for example, I know this single pane construction hasn't been used anywhere. So if I click on that, nothing gets highlighted. But if I click on the double pane here, which I know has been used, then those surfaces get highlighted. And that's very useful because if you end up importing something and one of the constructions has been applied to the wrong surface, the wrong building element type, or one of the surface types has come in incorrectly. If, for example, I click on interior wall and I see one of these outer edges highlighted, then I know right away that there's a problem and that one of my interior walls has come in as a external wall. Something's not quite right down. Then you can go and fix it. So that's extremely useful for model checking. So I'll simulate this now, because again, this is ready to go. Should be very quick. And this is our results viewer file. So in here, I'll have a look at the performance summary just to pick a day which is quite interesting to look at. So I can see the maximum air temperature happens on day 189, hour 13. But if I click on that and I click on load breakdown, I can see what is contributing to the zone temperature balance for that day. So here I can see, of course, the solar gain is quite significant because I've got those big windows. So they're a major source of heat. I can also see that we're losing heat through conduction through the windows as well to the outside, and I can see the effect of heat moving. This one shows you the effect of heat moving into adjacent spaces and into the fabric, and I can see equipment gains and things like that. And if I go to the visualization here, you can see all that information visualized. So, I could step through the hours and see how the dry bulb temperature of the zone changes. You can see the wind direction and magnitude, and you can pick from all these different variables. So, I said earlier that it has cooling set points specified. So if I click on cooling load and step through, I might have picked a day which is unoccupied. Yeah, I did. What day 190 there, we can see the cooling load reflected in the colors. And you can also view surface temperature results here as well. So if I click on one of these filters here, you can see all of the different types of results that you can see just in this results viewer, both visually and in a tabular form or graphical form. So there's lots of information here, and all that's accessible via the API as well, which is quite useful. So yeah, from here you can go and do building regulations, generate various reports, things like that. Sorry, you
we actually, yeah, I was just about to say we actually use these APIs ourselves internally, don't we, for the macros that do all of the sort of regulatory calcs,
exactly.
etc. Yeah,
exactly. So let's leave TSD for now and go back to Rhino. So one thing I would like to show you as well is, one of the reasons that you might be using Rhino is because it's very good for parametric design. I'm going to turn this off here. And I've got the exact same script that I showed you just now. This is the exact same Grasshopper script, but instead of going from model to IDF, just from model to IDF, I've added some extra components. So if I turn, let me just make sure everything's set correctly. If I turn this on, again, it's the same model, but instead of just producing an IDF and leaving it at that, I've got these extra components here. So I've got one here which takes the IDF file that was produced by the OSN component and imports it into TAS, and then that will generate the T3D and TBD for us automatically. And then I've got this component here which takes the TBD that was generated from the previous component and actually simulates it. And then from there, I have another component which extracts the annual cooling result. And then I have another component which manipulates those results into the format that can be displayed by color rooms. So I'll just turn that on.
So sorry, just to be clear, Andrew, I'm not an expert or even a beginner where Rhino is concerned, but each of those components are effectively using our API to get the work done. So it's
exactly.
Okay,
exactly.
So it's like a scripting environment.
Yeah, exactly. So I'll show you what the code looks like for that in just a second. So I'll just run this one now, and it will create those files for us. Sometimes it can take a couple of seconds to run. Yeah, it's a shame that this version of Grasshopper is not multi-threaded, but this is finished running now. So I'm just going to lock the canvas, lock the solver. So if we look in our Rhino model, I turn off let me turn off that visualization temporarily. Then we can see the cooling result has been drawn back into Rhino for us, which is quite nice. So you can see, obviously these zones with the windows have the highest cooling demand. And what you can do as well is you can, if, for example, I take this color rooms. So color rooms is actually one of the Honeybee Energy visualization components. So what I've done is I've just written something that links the two together.
Okay,
so I didn't have to write this bit.
Sorry, Andrew, I got to keep asking the questions. So this is basically just removing the building simulation part of the Honeybee process and replacing that with TAS ultimately. Okay, good.
Exactly, because if you're doing parametric design, then what you usually want to do is you want to tweak your design and then see the effect quite quickly without having to go through too many hoops. So what I'm going to do now is I'm just going to bake this geometry quickly. There's probably a better way of doing this, but I'm just going to bake this quickly, and then I'm going to move it over there. There we go. And then I can turn that pathway off and turn the visualization back on and unlock the solver. And then I can change something. So say, for example, we change the openable area of the windows. We make the windows much bigger. And then if I run this again, what it will do is it will again do the same thing. It's changed the window, so it will re-import the IDF file. It will recreate the building simulator file. It will re-simulate, and then it will extract the results. It will create that header so that the Honeybee color by rooms object understands how to present the data, and then we should see it appear back here in the plan. So I think that's finished. And if I turn off preview, lock the solver so I don't slow it down by accident. So yeah, here we can see the result with the much larger windows. So you can see the cooling demand is bigger. So that again, so this is just one thing that's possible. There's quite a lot that you can do with the API. If I jump back to my PowerPoint presentation, then yeah, like I said, the API is very powerful and flexible because it's been in the UI, been in the software since the beginning, and it mirrors the UI actions, which makes it quite intuitive to use. And using it, you can create things like Grasshopper plugins. We've had customers create Rhino plugins, Excel macros. I've made AutoCAD plugins, and you can have completely standalone utility applications. And as Ian said earlier, we use our API extremely extensively. Quite a lot of our applications that we ship with our software uses our API. I mean, that's how our 3D modeler actually puts geometry into the building simulator. So it's very well tested, and we understand it very well. We can support it, and there's not a lot that you can't do in it, that you can do in the UI. So just to show you what the code might look like, and just to emphasize this point that it mirrors the UI actions, I'll show you what the source code of this TAS simulate TBD component looks like that I used as part of that demo just now. So if you imagine how you would open a TBD and simulate it, what you do is you'd open the building simulator, you'd open your TAS TBD file, and then you just press simulate. That's what you'd have to do. So if we look at the code, this is what the code looks like. So line 90 here, we just open the TBD file, essentially. 91, we open our specific document. And line 98, we simulate. And then on line 105, I just add a comment here so we can see what the result of our simulation is and just check that everything worked okay. So, it is actually quite intuitive. And, we do support our API as well. So if you wanted to have a go at making a component, or if you wanted any of the components that I've demonstrated today, just get in touch and I'll send them across. And then before I pass over to Ian again, what I'll do is I'll just show you the geometry that Ian's going to demo in the CFD application, because I did actually make it for him earlier.
I'm glad you're going there, Andrew, because I was thinking my dome doesn't look anything like that rectangular office.
Yeah, so I made this quite a simple dome here. Let me turn off the Honeybee geometry temporarily. So that's the dome I've made. Let me turn this off. Oops. There we go. Turn that on. So yeah, I made this quite a simple dome hemisphere here, and then. Yeah, so what I've done is I've made the simple hemisphere, and then this yellow area here, this is going to be transparent, this is going to be double glazing, and then the top here is going to be opaque. So, we'll see that in the CFD results. But yeah, just to say, we can import all sorts of sizes of geometry. On one of the earlier slides, you saw a replica of St. Mary's Axe or something like it, and that came through okay, and it seemed to simulate quite well. So I'll pass back over to Ian now.
Yeah, do I have to hit share?
If you want to share your screen, do you want to show any of these slides first? I think you've got a couple.
Oh, God, have I? I think you're probably right.
So, for example, what's Ambience 3D?
Oh, gosh, yeah, okay. Yep, sorry, I'm reading through my notes here. Are we on page 11, by the way?
12.
Okay. Well, I'm going to go 11 and 12 then. Anyway, most CFD packages, current packages, use pressure correction, which is a way to try and conserve mass, but it's quite unstable, I think is a nice way of putting it. And clearly mass error tends to be linear and directional, so you tend to have an imbalance in mass in one direction, whereas pressure is obviously omnidirectional. So I spent a lot of my life trying to get pressure correction to work, and eventually sort of thought there's got to be a better way of doing this, which is why we ended up coming up with our own sort of internal or in-house CFD calculation methodology that implicitly conserves mass, pressure correction's gone, and you obviously reap the benefits of stability without the headaches and the pain. The second thing is that typically, I think we can play this video, can't we? I can't,
I think
you might
just
be
play
able
this
to.
now, but I'll play it again.
Oh, sorry, I was reading from my notes. Yeah, anyway, typically CFD calculations are steady states. That's just a single snapshot of a design day, so one point in time. And again, generally speaking, there isn't more time because the other packages don't tend to run terribly well dynamically. Ambience 3D was written specifically for dynamic analysis of a built environment. So what you can see there is a flat in London, quite close to Brentford, and what the software can do is take the surface temperatures, aperture airflows, and import those hour by hour through a whole day. So rather than just looking at a snapshot at say 2 p.m. where you've got your peak cooling condition or your peak heating condition, you can actually import the surface temperatures from the building simulation results and look through a period of the day, which hopefully is more useful. And a lot of the work that we've been seeing lately is where people are concerned about comfort and downdrafts and, you know, dynamic aspects of that local environment. You know, excuse me, are there going to be cold spots? Are there going to be hot spots? And being able to predict, you know, how bad they'll be, how long they'll last, and where they are is actually something that we're being asked to do more of at the moment. Yeah, we've got obviously air temperatures, you've got the air movement, the speed, etc., etc. We can do stuff like PPD and other comfort criteria. At the moment, we only do the one mass fraction. I think we're going to come on to that a bit later on. But yeah, relative humidity and CO2 levels are something that we can take a crack at. And now I'm going to share screen and hopefully. Yeah, can you see that? Give me a nod, Andrew. Great. Yeah. So I'm just going to quickly import. This is something we set up yesterday evening. I would like to import what Andrew just made or showed you in terms of the dome, but yeah, this is something we did yesterday evening. And normally you'd see a huge list of zones here, but because it's just a dome with just that one zone in it, it's not so bad. And down here at the bottom, you can select which day you want to take a look at. So I'm going to go with day 192, and I'm going to go from hour 10 to hour 15. And what we can do is take a step shorter than an hour, but at the moment I'm just going to update the surface temperatures every hour. And I think a cell dimension of 0.1 works pretty quick.
Yeah, it's 10 centimeters.
Yeah, which isn't a huge cell size,
yeah.
But yeah.
But the dome, I think, is 10 meters across, so it's a fairly large dome.
Yeah. So I just say okay to that. Hopefully we'll see the dome spring into life. Yeah, if I just maximize that. So I'm just using simple mouse movements to do the zoom and pan sort of stuff. I'm going to turn off this ISO surface to start with, and I'm probably going to kill off the X and Z planes. So I've just got one plane to look at. And then if I just hit go, basically, it's interesting. The air movement in a space does actually have a sort of, what would you call it, preconditioning requirement of its own. So yeah, you can see the hot stuff zooming up pretty quickly. So if I nip that up, it's going to get hot in there, by the way. So I'm going to go 35.
Yeah, it is a glass dome, isn't it?
Yep, and I think this is quite a sunny day. And again, you can change the temperature scale so you can see pretty much what's going on. Yeah, just go up 24. It's just going to get hotter in there. And again, buoyancy forces, and I think what are we at? We're at 11 minutes, 12 minutes. So in the top left there, you can see the elapsed time, and also, sorry, in the main area, you can see elapsed time versus simulated time. So we're at 10:17 in the morning at the moment. And yeah, fairly obviously, you've got hot air stratifying right towards the top of the space. This is running a lot slower because I'm sharing the screen, by the way. Yeah.
Yeah, a lot of the compute power goes to updating the render as well, you know, updating the visualization.
I think the render plus the fact that it's sharing the screen is definitely slowing things down quite significantly compared to what I was seeing earlier. Yeah, I definitely need to lift the bottom up as well. We really need spinners on these things so that you can see what's going on a lot quicker.
Yeah, you don't want to. Yeah, I think you've got 267 is the.
Yeah. Yeah. Yeah, still I probably ought to push that up a little bit higher as well. Anyway, you get the idea. Where are we at? 44 minutes, 45 minutes. So hopefully at the hour, we're going to see some interesting stuff start to happen. If you look at the floor, you can see the sort of Bernard cell type patterns. I'm a bit late to turn that on. I'm sorry about that. But you've got the classic sort of the colder air in this instance. Let's go up a bit. Oh, there you go. Yeah. So you've got the hot stuff coming up the sides. Yeah, okay, that makes sense. That makes sense. So I'm used to seeing the ones, the simulations we've done with these. And sorry, yeah, you can spin stuff around quite happily. That obviously slows stuff down a bit, so perhaps not ideal. And then we've just hit the hour barrier. And this resolving boundaries thing is where it's taking the surface information from the TSD, the building simulation, pulling that into the CFD and then changing the boundaries, which is why you can see the floors got hotter. And as I say, we can interpolate that every sort of 5-10 minutes. Oh God, wrong one. I have to go up to 45. Let's give that a shot. And again, what's interesting, if you look at, we've actually got a result. I'll turn that Y one off. We've got a result where we've got a perfectly symmetrical dome, and what you can see here is that red stuff on the right-hand side. That's obviously the hotter side where the sunshine is, and it just biases the whole sort of cooler areas of the dome onto the other side. Whereas if you look at the sort of perfect, in inverted commas, I'll quickly show you this now. If you look at the perfect dome with a completely flat floor and a completely set temperature for the actual surface of the dome itself, you get something that's almost completely symmetrical. Again, this is a horizontal slice just very slightly off the floor. So again, you can sort of see the Bernard cell formations similar to what we've got in that one that's running at the moment. And again, something I'm really pleased with this, because false diffusion is a very big thing in CFD, and I'd sort of expect to see the, you know, a bias towards east-west or north-south, or maybe even northeast-southwest, you know. But if you just stick a circle, and I actually use paint to do this, stick a circle on it, and it's pretty much spot on. So, you know, we're a fifth order rather than third order sort of calculation, so that's the reason for that. Right, I'm gonna have to whack the temperatures right up. Yep, too far. Yeah, we really need spinny wheels, don't we? Where am I going with this one?
Yeah, the final user interface
higher,
is probably going to look quite a bit different to this, isn't it, Ian? Because this is just our, if you haven't seen ambience before, it's our pre-release. So we've got quite a lot of work to do left on the UI.
I think it's pre-alpha release, if you're going to be brutally honest about it. Yeah. So I need more blue, which means I need to push the lower temperature up even higher. Let's go 43. It's probably too far. Yeah, I got ish. Again, let's turn the Z off. You can see these biases, you know, towards the areas. Still not enough dark blue in there. Does that mean I need to push it even higher, don't I? Oh God, too far. As I say, we need spinners for these.
Yeah, I just saw Gareth's comment pop up, and yeah, I was thinking the same thing about having a more intelligent sort of automatic selection based on the percentiles. Yeah, exactly. But
yeah, we funnily enough,
that'll come.
Yeah, we did have that in the original 2D ambient, so that it would literally take each of the color bands and then choose the band. This is all linear, by the way, so if you go 20 to 40, that's it, you're going to get 2-degree steps or whatever, whereas this used to change the banding so that it would give you an even distribution of color, so each color band was equally represented. Yeah, but this is purely consultancy at the moment, by the way. You know, this isn't going out into the real world other than in our hands for some time. And yeah, again, you can go into sort of eyeball explosion mode. So you can have two sets of Z slices, but it gets really sort of tricky to see what the hell's going on. And most of this visualization is done using VTK, the visualization toolkit. Yeah, it just starts to go, drives you mad. And again, draw your attention to the fact, what are we at? Elapsed time 3 hours. So we're going at a fair speed, and it will go a lot quicker if I wasn't sharing the screen and pulling a load of GPU, you know, drawing stuff and CPU drawing stuff. Yeah, it's all right. 5 minutes, 6 minutes, 7 minutes. Yeah, it was going a lot faster than that earlier. And you can see the mean temperature is crazy, 47.7, but that's very much in keeping with the building simulation that came before it.
Yeah, this dome doesn't have any apertures in it at the moment, but if we had apertures, then you'd be able to see the inlet streamlines and things like that as well, which yeah, that's quite useful.
I'm not sure I dare press this. No, I don't dare press that. You can get some very nice contour images out but yeah, I'm not quite sure why that isn't working. Yeah, just turn all of these off for a second. And if we look at the ISO surface, so this is literally just drawing a surface at this temperature. So it's spotting, it looks like it's moving. All I'm doing is just changing the value, and it's just displaying all of the surfaces which are at that particular value. So as we get obviously colder, yeah, we're not hitting anything at that point. And you can see obviously that as the thing is dynamically running, you're getting to see, I'm pretty sure if we go hot enough, there you go. It's mainly on that side. Yeah, this is one instance where the hot floor model is much nicer because you've got that flat hot surface at the bottom, and you can see a lot more of the sorts of cell formations that you'd expect. But it's useful. You know, it's a useful feature. And I think, yeah, enable mean surface, so you can just look at the mean surface, and obviously that's the temp 48. My God, yeah, it's pretty crazy. And how that's adapting. Yep. I mean, is that enough, Nagman, or I can do the quick office?
Yeah, perfect. Absolutely perfect. Let's switch back to the slides and take some questions.
Okay, I'll stop sharing. Sorry.
We've got a few minutes left. That was fantastic. Thank you, Ian. Let's thank you everyone for posting questions. Keep them coming. What we'll do is send a recording of this webinar and some additional resources in a follow-up email. So if you've registered and attended this webinar, you'll get that email this week. And any questions we can't answer, we always commit to answering in that follow-up email. So let's start. Let's go back to the Rhino and Honeybee workflow that we saw first, take some of those questions. So Andrew, I predicted this question would come. I'm not trying to take credit. These scripts that you've shown, right?
Yeah.
People are itching to use them. How, when, what, why, how much?
How to get them?
What's the general consensus there? Yeah.
Yeah, if you want access to those scripts that I've written, they're currently not part of the installer, but if you want them, just send me an email and I can send them to you. They're very easy to put on your machine. Actually creating your own script is very easy in Grasshopper if you haven't done it before. All you have to do is double click somewhere and type in C# scripts, and then you can double click on it and add your code. So then what I can do is I can either send you the code or I can just send you the component, and you can just add that to a folder on your computer and it will appear here as a component. So I've added them to my user library, which you can see somewhere here. User, there we go. So I've got just some TAS components that I've added here. There's another one which I meant to mention and I forgot to mention. So the default GBXML dump from Honeybee, because Energy Plus doesn't understand air walls, they're not supposed to type Energy Plus. As far as I'm aware, they don't come through to the GBXML, but I've written a modified version of that component which preserves the air boundaries so that they do come through in TAS as null walls. So again, if you want that, just drop me an email.
And a sack of money.
Perfect. Thank you, Andrew. What we'll do is we'll write up and share some of these examples of what script to use when and what the relative benefits are. You know, the GBXML, the IDF route, right? Because I think that's really interesting and people might want to try all of them, especially the one you showed where you're bringing results straight back into Rhino, Andrew. I think that was really, that was new to me. That was the first time I'd seen it as well, the TAS. Andrew, for a couple of people who are new to TAS, you mentioned a bit about the 3D modeler and the use of the API. So if you could just elaborate on that, how easy, what would someone use the API for when it comes to the 3D modeler? And also, we have another question about, can you import DWG files into TAS 3D?
Oh, yes, I meant to show you that. I must have forgotten. So I'll show you that very quickly. I have a layer here called shade buildings. There we go. So if I click on these two objects and then click File, Export with Origin, then press Enter to use the world origin, then I can pick AutoCAD Drawing Exchange, and I can, if I click Options here and make sure it's set to 2007 solids, then I can export my shade buildings. So I'm going to call them shade. Save that file path, and then when I'm in the 3D modeler, let's hope I still have my GBXML. Yes, let's just re-import that very quickly. So when I'm in the 3D modeler, I can press this button, 3D DWG, shade surfaces. And then if I give it my DXF file, then I can import my shade surfaces very easily, and I can reposition these and you know, I can use this again to do shadow analysis. For example, if I turn on the analysis model and do view, then I can look at the shadows and things like that, do daylight calculations, and they'll be taken into consideration. So to answer your question about the API in TAS, probably you use it for importing geometry. You could also use it for daylight calculations and shading calculations. If you wanted to do, yeah, exactly. If you want to do anything more advanced in terms of geometry, then you might as well just use the TBD, the Building Simulator API, because that's what TAS 3D uses to get geometry to the Building Simulator, right? So you might as well write your geometry straight to TBD, and then it's limitless in what you can do.
Amazing. And if someone's a expert Rhino user, they've been using Rhino for a long time, what kind of tips and tricks would you recommend to get your geometry in Rhino ready for building simulation, specifically in TAS, but energy modeling in general? So correcting 3D models in Rhino to make that process really easy.
Yeah, I would probably look at the Honeybee support. It depends what tool you're using. So if you're using pollination, your workflow might be very different, because I know that, you know, they've taken a slightly different approach, and they guarantee imports. So I can only assume that their IDF files and GBXML files are very robust generally. The ones that I've seen from TAS have been from Honeybee have been pretty robust. So there isn't really a lot that you need to do other than just to make sure that you've got, you know, complete enclosed spaces. You haven't got small gaps between your blocks that you've imported. So for example, I like to make sure that I've got grid snap switched on, and I also like to make sure I've got object snap switched on in certain circumstances, just to make sure that you've got a good Honeybee model. But if you visualize your Honeybee geometry and inspect it in Rhino before you then attempt to generate the GBXML, it'll be very quick and easy to identify any issues that have arisen as a result of it.
And what about shades in NG+, if you're importing that directly, IDF into TBD?
I haven't really tried external shades. I tried internal shades using Honeybee, and they didn't come through. But again, you can do the 3D shade surface import for that. So you could just actually draw them in Rhino and then export them as solids and then import them straight into TAS 3D, and they'll have the shading effect that you want. External shades will probably come through. As long as they come into the GBXML file, they'll come through. But as I'm not an expert in NG+, I'm not sure whether or not it supports external shades in GBXML.
Yeah. Perfect. Let me quickly respond to a few chat comments. So yes, you'll get a recording and some follow-up resources from this webinar. And Mustafa, thank you for your comment about the air boundaries. That'd be great if we can take a closer look at that, and then we can follow up and get back to everyone together on that. We had someone asking about GenOpt, because you mentioned it earlier on, I think in one of the visual slide. What if you could just briefly say what is that in high level, and how does someone get access to that?
Yeah, so GenOpt comes as part of the software. I was trying to find the relevant slide now. Yeah, it comes as part of the software, and it basically allows you to vary parameters via our APIs based on constraints that you specify, and it will do that in an intelligent way. So you can do, you know, your standard parametric design where you just simulate every single possible combination of variables, but that can result in a ridiculous number of simulations very quickly. Or with GenOpt, you can say, okay, I want to optimize using a certain algorithm, and it will try and minimize the number of simulations and work its way down the representation of and find the local minima by varying those parameters. So again, anything that you can change in the UI, you can optimize. All you have to do is write a cost function. So a common one might be to try and optimize the simultaneous heating and cooling load, and then you can vary U values, ventilation, you can vary window. If you've got mixed modes, you can vary the set point of your windows to try and reduce your annual total consumption, for example. So that's one case where you might want to use GenOpt. But yeah, it's included in the software. Everyone's got access to it if they've got TAS.
Perfect. Very powerful. Let's take a couple of questions on the CFD, Ian. So two questions just to consolidate multiple questions together. One is, if someone has a project they might want to use Ambience 3D on, what's the way to get started working with Ambience 3D? And the second is specifically about air quality, and this goes back to that ASHRAE standard on infectious aerosols we were talking about. How could you model pollutants, particulates, and what kind of outputs, and why is this software really useful compared to just a generic CFD software out there?
Okay, at the moment Ambience is purely consultancy. So the best thing you can do is produce a decent 3D TAS model, a decent building simulation model, potentially a plant TPD TAS systems file, and then we can make use of that to do the airflow analysis on your behalf. So not a user tool at the moment, although there are some users out there with alpha versions. So yeah, but that'll be coming in the next 6-9 months. At the moment, what we want to do is knock off all the rough edges in-house on these sorts of consultancy jobs, which will obviously lead the software hopefully to a much more productive sort of form. What was the other one was mass fraction, basically, wasn't it? So at the moment, we've only got
and air quality.
Yeah, at the moment we've only got one mass fraction, which defaults to well, basically water vapor or fraction of water vapor, so we can predict RH, but there's a very quick switch where we just turn the RH off and turn on CO2, and there's no reason, as long as you've got the physical parameters for the mass fraction, we can include it. And people will be sitting there thinking, why don't you just put them both in there? The problem is every variable you put in the cell, and every cell, if you imagine it, you know, millions and millions of these cells, even if you increase the cell size, the individual cell size by, you know, 10-15%, that's a big difference when it comes to the size of the overall file. So we can do both, but generally we've just got the one mass fraction at the moment, and we either have that working as relative humidity or water vapor concentration, or as I say, we can do CO2. We've done CO2 before. And yeah, a very frequent thing we've seen is, you know, what are the CO2 concentrations in classrooms? Do we have downdrafts in classrooms? For some reason in the UK at the moment, schools seem to be getting a lot of attention in terms of comfort. And obviously comfort, you know, it can be simple temperature, it can be downdrafts, or
I think that's really interesting. Yeah, because you know, these tools, Rhino, Grasshopper, a lot of people use them to be very creative and design very complex building shapes as well as very simple shapes. But the CFD has always been quite difficult, computationally intensive, very time consuming, very tedious, hard to use, right? With this, you're bringing in an element where it's dynamic, hourly, which is unique in itself, the CFD simulation.
It's actually seconds and minutes, but yeah, we interpolate the hourly building data. But and this, again, you know, I'm hopefully not giving away too much, but the reason the CFD is so quick, it moderates the way the code is working so that we maintain stability, but obviously add that dynamic element to it, but keep the stability. Yeah.
Brilliant. Thank you everyone for the questions. I'll just hand back to Ian for some closing remarks quickly. Thank you for people contributing to the Q&A and chat. We will write up these answers as well in the following up email and share a recording to this webinar. Gareth, thank you. I'm going to upgrade you to speaker next time. Appreciate your help and comments there. Thank you. Andrew, fantastic demo on the you know, the Rhino, Honeybee, Grasshopper, TAS and back. Really, I learned a lot about TAS right now watching you in this live presentation. And Ian, the CFD is just so exciting. We have so much more to tell about the CFD, and we'll be doing that in the new year. Thank you. I'll hand to Ian for some closing remarks.
Yeah, thanks for dumping that on me now. Yeah, no, it's been a pleasure. As I say, the CFD is weird because we've actually had it for probably 5-10 plus years. The big difference is the fact we've now got the visualization stuff taped, so we can actually look at those results and get those answers out into the you know, engineering fraternity in a meaningful way. The big change as well is being able to read in a lot of the TSD information directly. So if you've got a good TAS model, then running CFD really won't be that much of a chore. So yeah, please, if you've got projects which might benefit, you think, from having some CFD work done on it, and you've got the TAS models available to yourselves, please let us know. It won't cost you as much as you might think compared to the sort of generic CFD packages and the timescales and the pain involved. And you know, we should be able to do the best part of a day. Not that long. Again, it depends. You know, if you've got a massive great atrium or giant football stadium, yeah, it's going to take a long time. But if you've got a classroom, I mean, you're talking an hour or two maximum. So yeah, it's very, very quick and straightforward. Hopefully a big change.
Brilliant. Thanks everyone for joining, and we will be in touch with further information and videos and recordings. This might be the last webinar EDSL hosts this side of Christmas. So from everyone at EDSL, we hope you have a good holiday season, and we'll see you in the new year. Thank you.
Great. Thanks everyone. Cheers.
Bye.